Hello, good morning to everyone. We will start soon at 10:15. Hello, good morning to everyone. We will start soon. And you know that if you want to ask questions or raise your hand, there is a chat. And you can use this time to do a test with the chat. Otherwise, I have my Skype open on another computer, and you will be able to also make a Skype call to me if the question is too complex to be presented on the chat. Okay? Can you confirm, some of you can confirm that write a message on the chat so that we can make sure that you are able to interact with us. Tu vedi chat. Okay, yeah. So the audio is good. I learned. And we are all set. We will start at 10:15. La teniamo proprio giù così.
Mhm.
So, good morning to everyone. So we are starting this experimental way of lecturing. It will be slightly less efficient than in class, but you will have also the opportunity to review and see again what we will be presenting. And today, as I promised, we will do an exercise putting in practice most of the notions that we have seen so far. And my collaborator Gael Cascioli, who is here, will show you first what the problem is, what we are dealing with, and then we'll show a Matlab code that solves that particular problem. Okay, and once again, if you have questions, please use the chat. I will take an eye on the chat, or use call me on Skype. I gave you also my Skype ID. Okay, so at this point, I will give you, Gael, the floor. It's important that you are able to see the cursor moving.
Mhm.
And could you please let me know if the cursor is moving? Yes, I see it on my side screen. Perfect. So let us start. Gael.
Good morning, everyone. I'm Gael Cascioli. Here I show you my email. If you need, in general, some questions and help for this course, you just have to write me at this email here. And today we will see an exercise that applies, as Professor Luciano said, Professor Yes said, an exercise that puts in practice what you've learned so far. So, as you know, you've studied the orbit determination problem, that is no other than an estimation problem for which you can estimate some parameters of a dynamical model. So in general, this problem can be applied to any kind of problem, from a spacecraft to a vehicle, from everything that can be described with differential equations. So today, the particular problem that we will deal with, let's see if it fits in the screen, is a very simple, maybe the simplest second-order dynamical system, that is the spring mass system. Just a moment that okay, maybe the screen is cut. I will fit it in the screen. Okay, it should work. Let's see. Just a moment.
No.
Okay, more or less. So, again, if you have any kind of questions, just feel free to interrupt me, because I'm here for you. So if you don't understand, it's useless, okay? So the problem we're dealing with is a simple mass connected by two springs to some kind of wall, and it is oscillating. We have some measurements, in particular range and range rate, so the measurement of the distance and of the velocity on the line of sight. These measurements are taken from the point P and they measure the point Q, okay? So what we want to do is to estimate, as you know, the motion of an oscillator like this one is completely determined from its initial conditions, once the physical constants of the problem are fixed, such as, for example, K, the rigidity of the springs, and also M, the mass of the mass. So in this case, we want to estimate the initial conditions, so x0 and v0 of the mass spring system, by observing its motion, so by analyzing the observables that we have, so range and range rate. As you know, the equation of motion of the mass spring system can be written as you see here. So you can write just x double dot equals to some rigidity constant times x over n. If we call omega square this constant, the natural frequency of the system, we can simplify everything to the well-known second order equation for oscillators. So this is a second order system. As I said, we want to estimate the initial condition. So we want to set up a least square filter in order to do this. So in this case the problem is very easy because the solution of the mass spring system can be known quite easily analytically. So we don't need to integrate the differential equation, but we just need to compute its solution from the analytical expression. So as you know, computers like to work with first order systems and not with second order systems. So the first thing that we have to do is to rewrite this equation as a first order system. You should know how to do this because it's quite simple. It's done during the first courses that you have already passed. So you just write the state vector. Remember that the state vector is the vector that contains the parameter that we want to estimate. So in this case we write x of t, that is our state vector, composed of position and velocity. This allows us to write a first order system because as you can see here on the right, we can write x dot v dot equals to this matrix times x v of t. If you try to write this on paper, it's straightforward. You don't need to do derivatives because in this case, as you can see, this is the solution of the dynamical system. So we know it, as I said, and moreover, the most important, it is linear in the parameter in the state. It is linear in x0 and v0, meaning that we can already immediately write the equation x dot equals to ax instead of x dot equals to in general complex as you want function of x and t. In this case, the factorization with a matrix times the state is for free. It's already done. You can see it from here. This is the solution of the linear system. So you just need to write this in a matrix form. That is what you see here. So we have this matrix, that is the A matrix, that is 0, 1 minus omega square 0. So we have our first equation. As you know, the least square problem is composed of two equations. The first equation is the one for the state propagation, the state evolution, that is this one that we have already seen. And the second one is the observation equation. As you know, I have written it here somewhere, this one. Y, the observations, are equal to j, the function that describes them, that is a function of the state and of time, of course, plus epsilon, that is the error, observation noise in our case. Okay? So what we need to do, first of all, is to define this observation, to compute this observation. From the problem definition, you can see that it is quite easy to write the ranging observable. That is, in this case, you just use the Pythagorean theorem, as you can see from the sketch here. Rho is just, you compute this side of this triangle. So it's very easy because it's x squared plus h squared under square root. So what you can see here. For rho dot, we just remember that we have just computed rho, so we need to do the time derivative, and it's quite easy. You can do it with chain rule. So d rho over dt is d rho over dx times dx over dt. So it's quite easy computed. So these are the observables. Okay, I tell you again, if you have any question, just ask. Don't worry, don't feel shy. So these are the observables. Okay, in this case, as I said, the state propagation equation is linear. But what makes this problem non-linear, so for which we have to do a least square filter, as you know, we have to iterate the least square filter, is that our problem is not linear in the observation. As you can see here, we have a nonlinear function of x, while here also we have a nonlinear function of the state because they are multiplied together. So what we need to do is to linearize the observation equation. It's easy, you know how to do it, because here you have the expression. We know that y equals to g of xt. So if we linearize this, we get g of x star t, that is our linearization point. As you know, when you do, like, for example, a Taylor expansion, you have that the function is equals to its value on the linearization point plus some higher order terms. So in this case, we have the function y that is equal to its value on the linearization point, that is g of x star, we call the linearization point star t, plus its derivative times the delta x. Okay? So as you remember, the linear least squares problem works when we are near the true state, so the true trajectory in this case. As you remember, in for example, series expansion of function, for example, Taylor expansion, Maclaurin expansion, we linearize around a point because there are functions like algebraic expressions. In this case, we are dealing with differential equation. So in our case, the linearization point x is a function of time, so we call it trajectory. This is the reference trajectory. It is no other than the linearization point. So it is a trajectory, it is a point that we know quite well. Not perfectly, because otherwise we wouldn't need to estimate the problem, but it's quite accurate. So in this case, by recalling that we call the delta x small x, as you have in your textbooks and also in the slides. In this case, we call it delta x. It is the same thing. So from now on, when you see delta x, this one, it is the small x that you have on your textbook. So we have the linearized equation, because small y equals to h tilde times small x plus epsilon. Okay, how do we compute h tilde? It is written here. It's no other than the partial derivatives of g, that are the observables, with respect to the state. Okay, so it is easy because here we have the expression of y. You just have to compute the derivatives of this with respect to x and v, and this with respect to x and v. So we have the expression here. This is h tilde. You know, when you have such a derivative, a vector derivative, the element ij of this is the gi on the xj. So we have d rho on the x, d rho on the v, d rho dot on the x, and d rho dot on the v. It's you should know this. So if you do these computations, you get the h tilde matrix. Okay, so we are almost done because we have our linearized state equation, our linearized observation equation. However, as you have seen in the previous slide, here, this is y of t. So in this case, if we use this equation for each time at which we have the observations, we would have to solve for, if we have m observation, we would have to solve for m values of small x, of dx. So, but since we are dealing with a dynamical system, and since we know the time evolution of this dynamical system, we can relate all these small dx of t. Okay, you should see it better. We can relate all these dx of t with the so-called state transition matrix. The state transition matrix is defined as follows. So, phi, that is the state transition matrix that brings the state from t0 to t, is no other than the derivatives of the so-called variational equations, so of the equation written in the small deviations. That is what we have in the previous slide. These are variational equations because we are dealing with small deviation, that are these dx dot, dx, etc. So, in general, we can write that x of t equals to phi times x of 0, for example. So this is how we compute the state transition matrix. In general, the state transition matrix can be computed with its own time variation, with its own differential equation. That is this one, phi dot equals to a times phi. In this case, we are lucky because we don't need to integrate this equation since the solution of the state is known. So we just have to compute these derivatives because, again, as you have seen, the solution for the state is known, is analytical. So the derivatives with respect to x0, v0 can be done explicitly.
So let me add one thing. We said that there are two ways to compute the state transition matrix. In general, in a complex problem, you have to rely to the solution of the full differential equation. Phi dot is equal to A phi. When, however, an analytical solution is available, we use the meaning of the state transition matrix, that is, partial derivatives of the states at time t with respect to the state at time t0. And since here we have a full analytical expression for the state evolution, it's more convenient to compute the state transition matrix directly without doing the integration. I don't know, however, Gael, if later you have an example.
No, we will do it all analytical.
All analytical.
Yes, in later exercises, you will have the chance to integrate the equations. Don't worry, you will have to do it. In this case, you know that numerical integration always raises numerical errors. So, in this case, since we have the full analytical expressions, we are happy to compute them analytically. So, as I said, in this case,
there is a student who says that it's a bit too fast.
Okay, I will go slowly. Sorry. Okay, as Professor said, in this case we have the analytical expression. So we take the definition of the state transition matrix, that is the derivative of the state at time t with respect to the state at time t0. So it is easily computed. You know, as I said before, how to place the derivatives in the matrix. So we compute them and we have the analytical expressions for phi. Okay? So we are almost done because at this point we can relate all the observations to the same time, x0 for example. That is the time at which we want to estimate the state. Okay, so as I said at the beginning, we want to estimate the initial conditions. So if we call the initial time t0, we want to estimate the state x at time t0. Okay, so we can relate all the observations to time t0. In this case, we will have two kinds of observations, range and range rate, and we will organize them in a vector, in a column vector, as you see here. So for time t1, we have range and range rate. For time t2, we have range and range rate, and so on until the end of times. So also the H matrix will have to be organized in the same way. So as you see here, the first row of H tilde is relative to the range, while the second row of H tilde is relative to the range rate. Okay, so remember this because we will need it in the code. So at this point we can build the full mapping matrix, because you know that the least square filter works with, as I said before, two equations, the equation of the state and the equation of the observables, in which we write y equals to hx plus epsilon, where h is the full mapping matrix. So we have computed the h tilde, that are the partial derivatives at a certain time. As I said, we want to refer everything to x0. So remembering that x1 equals to phi times x0, we can just replace x1 with phi x0 and idem x2 with phi x0 and so on. And so we can have everything related at a certain time, that in our case is x0. So we will have our full mapping matrix, that is H, in this way. So we have to compute separately H tilde, phi, multiply them together, and so we have the full mapping matrix. Okay, now we are ready to run the filter. So, well, to set up the filter. So please, if you have any questions until now, please ask before I go on, so it's easier to answer to your question eventually. And okay.
Yes, let us wait a couple of
Yes.
minutes
Okay.
for questions that may come also on Skype.
Okay.
So, no question.
No
Okay,
questions. We can go
let's
on.
move on.
Okay. So, as I was saying, you know that from theory that the solution of the least square filter, meaning that the deviation of the state, because remember, in least square filters we always deal with deviation of the state, not with the state himself. So what, as I said before, it's the small x in the slides and in the book, and it's called here delta x, okay? In this case, just ignore the part about a priori informations. We will do it in a later lesson. In this case, we will not use a priori information. So, as you know, the solution for the state deviation equals to h transpose wh to the minus 1, here it's missing, times h transpose wy. So this is all we have to do. In this case, of course, you don't know the a priori because we are starting from an unknown solution. So, at each iteration of the filter, you have to solve for this equation. So, again, x transpose wh to the minus 1 times h transpose wy. You compute the state deviation delta x 0. You estimate with the hat, remember it's an estimate. You estimate the state deviation, and so you can update the state with this deviation that you have just computed. So you run again the filter with the updated initial condition, that is this one, so the original one plus the deviation that you have just computed, and you iterate the filter this way, every time updating the reference solution, the reference trajectory, remember the linearization point, until you reach convergence. We will see it all in detail, don't worry about that, we will see the code, it will be more clear. You might ask yourself, when do I stop the filter? We will go through that. There are some easy criteria. So, first of all, what you expect from the residuals, meaning that, remember, the residuals are y, so the difference between observed and computed observables. Okay, so in principle, if your dynamical model was perfect, described perfectly the system that you are observing, what you should see in the difference between the observed observables and the computed observables should be only the measurement noise. In our case, the main assumption is that noise is white, so you should know what white noise is. So you should see in the residuals only white noise. If this is not true, you would see something else in the residuals. That is the difference between observed behavior of the system and the computed behavior of the system. So, in general, you will iterate your filter until you get only observation noise. Okay, so when you have a small amount of data, you have time to do it, you just do this way. So it is what we will do now. So you just look at the residuals, you see the shape of the residuals, and you can conclude just, let's say, qualitatively, if the filter has converged. However, there are more...
I want to add something about white noise, a concept that we have not yet introduced. White noise is a noise where each sample is uncorrelated from all other samples. In general, in orbit determination, as in many other applications, one speaks of AWGN, additive white Gaussian noise, which is a noise which follows the random error distribution, the bell-shaped curve, and all the data are uncorrelated from each other. So it's a simplification, a strong simplification. It allows to do simple calculations, but it's not only the truth. So in this course, we will use always this assumption, additive white Gaussian noise, okay? Which means that the weight matrices are also diagonal, and all the elements outside the diagonal are zero, as we said in the last lecture.
Okay, so I was saying there are also some quantitative means to verify if the filter has converged or not, and we will see them here. So in general, the filter has converged when the further deviations of the state that you compute are small. So in general, what you have is that at first iterations you move the state quite a lot to fit the data. So having white noise in the residuals means fit the data, fit the model. So you fit your model to the observations. So, in general, at the first iteration, the state moves quite a lot in order to fit the model, and then when you have converged, the state is, let's say, correct, so it moves no more. And it is what is written here. So, the delta, so it is called delta iteration, means the difference between this iteration and the previous one, is very small. We will not talk for the moment about sigma, I will explain you later. So, as you know, what I have not said before is that here we have the weighting matrix, okay? You have still not studied the minimum variance estimate, but what I can tell you, trust me, for the moment, you will prove it mathematically later, is that if you choose the weights in a certain way, we will see it later, we will do an example, the estimate that you get is the minimum variance one. Meaning that you get an estimate of the state that is, let's say, the best one, the best possible one with the means you have. So, in particular, if you choose these weights correctly, in a way, let's say, again, that you will discover in the future, these are some criteria that you can use. First of all, the mean. Here you don't need the weights. So, what you want is that the mean of the residuals, since we are talking about white noise, the white noise has zero mean, we want that the residuals have the mean that is closest to zero as possible, okay? And this is what you can see here. So if you see during your iterations the behavior of the mean, it will go to zero if you are converging. Otherwise, it will diverge from zero. Another thing that you can see is the RMS, root mean square, okay? So it is the quadratic sum, quadratic mean in this case, so you can see in this case epsilon is the vector of the measurement noise that once you reach convergence should be equal, if you have converged, to the residuals, okay? So at convergence the residuals are only purely measurement noise, okay? So in this case epsilon and y are the same thing. So this is, as you can see, a scalar product, okay? It is epsilon transposed epsilon. So it is the quadratic sum of the residuals divided by the number of points. So it is just the root quadratic mean, okay? This should be equal to the sigma, in this case we talk about standard deviation of the observables. So the question can be why the root mean square should be equal to the standard deviation. These are in principle two different concepts, okay? The definition of the standard deviation, you should know it, I recall you. It is the same thing as you see here, but it is epsilon minus the expected value of epsilon transposed times epsilon minus the expected value of epsilon. So the value of the parameter minus its mean times the value of the parameter times minus its mean, sorry. In this case, and this is sigma, if we have converged, these two quantities are the same because the mean should be zero. So these are almost the same information, Okay, so coming to the weighted part, if you choose the weights, as I said you before, you will discover how, but in the minimum variance way, you should have also this information, meaning that, as you can see here, we have again a quadratic sum, epsilon transposed epsilon. This is again a scalar product, but here in between we have the weights, so this is a scalar product with matrix W. In this case, if you have chosen the weights correctly, first. Second, if you have converged, this quantity should be almost equal to the number of observations, okay? Don't worry if you don't have fully understood this now, we will see it in detail in the code. Okay?
But you can already understand why this must be equal to the number of points. Epsilon transpose epsilon is made up by terms which are the residuals square, epsilon I square, okay? Epsilon I square divided by its variance is a number of order unity, okay? So if you sum n numbers all of order unity, you get the number of points that you are summing, therefore the number of residuals. Of course, there will be residuals which are larger than the sigma, residuals which are smaller than the sigma, but on average, one must expect that the sum of square is equal to the number of points. Okay?
Yes, this is called the sum of squares, SOS. So, it was a brief introduction just to introduce you to the problem, and now we will see its practical implementation on Matlab. I will try to go very slow so you can understand everything. Don't try to replicate the code now on your computer, otherwise you will get probably lost in the explanation. The code is already available on the website, not this version, an older version, but it's actually the same. But we will make you available also this version of the code. So for the moment it's important that you see what I'm explaining and you listen to me, and then of course again if you have any question just stop me and I will be happy to answer. Ok, so
più piano.
Sorry, okay, I will go slower. Okay, so we have to set up a Matlab code that solves the problem we were talking about before. So the spring mass system and the estimation of its initial conditions. Okay, so as always, the first thing to do in Matlab is clear all, close all, etc. So you have no problems of variables already allocated and something that is uncontrollable. Okay, here I have a switch that allows us to choose which observations to use. We will use it later. For the moment, just ignore it. Okay, so this is our problem as we have seen before. So the first thing to do is to define the dynamical model of the spring, of the mass spring. Okay, so we have some constants that I give you here. We just define them. We have K1, K2, M, H, and W, that is defined directly from the previous ones. Sì.
Ce l'ho io.
Okay, sorry. So this is the constants of the dynamical model. Okay. Okay. So now we have said that we have everything we have to do is to fit the observable. So we need to have some observables. Okay. In this case, as in the real case, you have some observables. You don't know from which model they come. You don't know how they have been computed, but we have them in a text file. Okay. I can maybe show you the text file. It is this one. You can see it's just a text file made of time steps, range observations, range rate observations. Okay, the units are in international system once, so you have here seconds, meters, because this is range, and meters per second, because this is range rate, okay? So we can load an observables file by just the Matlab built-in function that is called load, and since it is tabulated, as I have shown you before, it will load in a matrix that has as many rows as the original file and as many columns as the original file, okay? So here the first column is the time t, so I just read the observation file, the first column, and the same thing with range and range rate, so the second column and the third column. In this case, we made it quite simple, so the number of range observables is the same number of the rate observables. So the number of points is just the length of the time, okay? So this was just to load the observation file. I show you this in detail because in the later exercises and homeworks you will have to do this, so just remember that it's super easy. You just use the load function of Matlab and then you divide and you split the things. There are other ways to do this in Matlab, like this is Matlab, you can do import data, and this is a graphical user interface to do the same exact thing. You do like this, Matlab reads the file, decides how it's working, and you can just, okay, import only this one, you give it a name, like range, and also to the others, you select everything, and you click to import. You should know how to do this already. Okay, so we have imported the observables. So since we know the dynamics of the dynamical model, okay, we know its differential equation, we know its solution, analytical solution, the first thing to do, of course, is to see if we need to estimate its initial condition. So to immediately check the observables, okay? So first of all, let's see if we have imported everything correctly. So we create a figure and we plot the range and the range rate. Okay, so I run every part so you can see it. I run also this one. Okay, so here we should see the observables here. We cannot see it super well, but if you do it this way, it works better. So here I just, as you can see here, taken the observables that I have loaded from file, okay, and plotted them, okay, just draw them. So you can see here that we have the range that is going this way. We have units of meters around 50 meters, so it is oscillating around 50 meters, while the range rate is oscillating around 0. Okay, this is something that we expected. This is just a mass spring, so we expect a sinusoidal behavior in general. And we expect that the velocity oscillates around 0 and the position oscillates around a quantity that is defined by the position of the observer. Okay, so it seems that I have imported everything correctly. I have not imported the time instead of the range and so on. Okay, so as I was saying, one important thing to do at first is to see the residuals. Okay, I've written here just the solution. It's the same thing that you have on the slides, just repeat it so we have it here and we do not get confused. Okay, so these are the initial conditions that we guess, because we have to start from a guess. We could start also from 0, 0, 10, 10, minus 20, minus 20, as you wish. In this case, we decide to start from a set of initial conditions because we need them to compute our trajectory. So, what we have to do at first, as I said, is let's compute the trajectory, let's compute the observables, and see what the residuals look like. Okay, so if we were lucky and we guessed the correct initial conditions, we wouldn't need to do anything because we would have already the correct initial conditions. So what I do is I compute these equations. They are exactly these ones. It's written here. As you can see, I've tried to use almost the same symbols. So what I do here, this is you already know it because Matlab always throws errors when you don't do it. It is always convenient to pre-allocate variables, okay? It is faster and more efficient. So in this case, you already know how many points will have your trajectories if you use the same times as the observables. Remember, these are the observables time, okay? So I just compute for I in equals 1 to length t, I just compute x, since I know its expression, and I compute v, since I know its expression, okay? I put it in the variables that I have defined before. So, as I said, let's compute the observables. You know the expressions. So again, it's very easy. I just compute the range, that is square root of h square plus x square, at each time, of course, and the range rate, that is this expression that we have here. So, let's compute immediately the residuals that are, I remember you, always O minus C, observed minus computed, okay? Remember this when you will be doing your homeworks, otherwise you will be spending days trying to put minuses around and you will not work it out. It's always observed minus computed. It's a definition, okay? It's a convention. So, these are the observables that I have loaded, remember, here. Here, there are these ones, the one that I've plotted here and the one that I've taken from the text files. So, range observation, rate observations, okay? So, if I go down, this is what I'm doing. Here, okay, so the range residuals are equals to the range observed minus the range computed. The computed is this one. The same for range rate, okay? So, in this case, again, I compute these sections. I don't remember if I've done it, so I will do it now, okay? Okay, this one too. Okay, these are the range residuals, and these other are the rate residuals. Okay, as I said, if your guess on the parameters you want to estimate was perfect, you should see only white noise. And this is not the case, because the white noise, as Professor said, is uncorrelated. So you should see no trends, no patterns at all in the residuals. In this case, you can see, I have not plotted the line, I will do it now. You can see that there is still a sinusoidal trend. That is actually what you would expect if you have an error in the motion of your spring mass system and you compare it with another spring mass system that is oscillating at another frequency, for example. It is not the case. In this case, it is only out of phase. You would see a sinusoidal behavior, as you can see here, and also in the range rate, okay? So, let's do it just to see it better. I just put a line here. And also here. And you should see this better, this pattern better, here. Okay, so the rate is computing. You can see that this is what you want, but not white noise. Okay, so we are legitimate to run our least square filter. We want to estimate the initial conditions that lead us to only noise in the residuals. So we want to estimate.
This is the second iteration of the phase.
No, this is prior to running the filter. Just to check.
Just to start from initial condition, best guess.
That's it. Someone told us that
leads us to a very unsatisfactory trajectory.
Of course, because as you can see, the error in the trajectory, again, maybe I have it here, yes. If you use these initial conditions that you have taken from somewhere, you have guessed, someone told you, you have an error in range that amounts to 0.01 meters, but also to 10 centimeters more or less, and in range, okay, in the radial position, while in the radial velocity you have an error of this order, okay? So we have to run the filter. So remember, these are our equations, just to recall it, and we have to solve this equation here, okay? X hat, that is the deviation that we have to add to our initial guess of the initial condition, equals to this expression. Okay, so before being able to run all the iterations, we have of course to define all these terms. So let's do it step by step. Again, if you want to stop me with no problems, okay?
Well, there is 1 minute left, 2 minutes left
okay,
before
okay.
the break.
We can do it after the break.
It's up to you, but go ahead and try to
okay,
explain.
I just explained the overall here. So again, the suggestion that I give you is always try to pre-allocate variables, okay? Because otherwise you will always end up in some errors in which you don't know why that matrix has those dimensions, etc. Okay? So in this case, as I said, we have to iterate the filter. So we have to define how many iterations we will use. So in this case, I define 4 iterations. Maybe we'll need more, maybe we'll need less, we will see. We will do many cases. So in this case, the x0 guess, so the first one that I use, is equals to x0, v0. That are the ones that I have defined before. It is 4 meters, if I recall correctly, and 1 meter per second. They are wrong, as we know. Okay, but we want to run the filter. So, as you can see here, the problem that we will set up is a weighted problem. You know that we have to use the weights to take into account the relative weight of the observations, okay? It might happen for several reasons. For example, if you have only one kind of observation, for example, range or range rate, but only one kind, you do it, for example, to take into account differences between receiving stations. Maybe one station is more accurate than the other. Or, for example, differences in the weather conditions in the real case. The weather can introduce a good amount of noise on the radiometric observations, okay? So you can use the weighting matrix to take into account this, in order just to be confident on what you're doing. You don't want to give too much trust to observations that you already know that are not very good, but you want to include them because maybe they can give you a small contribution that it is always useful. When you have two kinds of observations, as in this case, so we are using range and range rate, it is mandatory to use the weighting matrix in order to discriminate between observations. They can be, in a general sense, accurate in the same way, but accurate in the same way doesn't mean anything, okay? So for a standard accuracy for range can be 1 meter, while 1 meter per second is really a lot for current range rate systems. So you have to use the weighting matrix to give the differential weight to the two kinds of observations, and so to give them also units of measure. Okay, we will see it later, and we will see why this is important. So remember, we have to define some weights, and then I will stop for the break. For the moment, we know nothing about the observation. Suppose that we don't want to do a weighted least square, and we just select the weight equals to 1 for both. Okay, so at first attempt, this is what we do. We don't know nothing, we know nothing, and so we select a generic weight that is 1. Okay, let's do the break and we will continue later. If you have questions, this is the good moment to
remember that if you do this, you have to process the data individually. You cannot mix range and range rates. Okay? So, anyway, we are here taking questions also on Skype if necessary. And we will reconvene at 10, 11, 17. Okay? And in the meanwhile, we'll take questions.
Okay, here we are again. We've received 2 questions during the break. The first one is on the YouTube chat. We've received 2 questions. The first one is on the YouTube chat, and it is, can you explain again why we take weights randomly? Okay, for the moment it is not totally randomly, because we take the same weight for range and range rate, because for the moment the reason for which I take them this way is that I want to see what happens without weights. Saying 1, it means that we are using here for W an identity matrix, okay? So it is as if I wasn't using the weights, because I will introduce them later. In general, the selection of the weights is a tricky task, and we will deal with it later, okay?
But if you remember, at the last class, I showed you examples of residuals. And we saw that not only the RMS value of the residuals was different from station to station, but even during a single tracking pass, the residuals could be different. And in that case, the obvious solution is to attribute a weight to each data point. So all the data acquired in good conditions have a large weight. The data acquired in poor weather conditions, I showed you the example of the wind, those residuals must be deweighted and therefore be attributed a different weight. So the residuals are not chosen, the weights are not chosen by chance. They are chosen according to the RMS value of the residuals once we are at convergence, according to the variability of the time series. The time series of the residuals is non-stationary, and we have to take into account that attributing different weights to different pieces of the observable quantities.
Okay, so we will see it.
Am I ok? Il video si vede sfocato.
No, dice risolto.
Ah, risolto. And can you tell me whether this answer is satisfactory or not? Brandizzi. Okay, thank you.
Okay, so now during this hour, 40 minutes, we will see how to implement the filter. Okay, so let's start. So as I said, I will pre-allocate some variables here that I will use later. These are only technical things. Okay, we have already discussed the weights. Here I have saved some values that will be important later. We will see them later. So the first thing to do is to initialize our state. Okay, so the initial conditions. In this case, I have defined above the values, the first guess values of x0 and v0, and I use them, I save them. As you can see here, I highlight x0, and it is the variable that I use inside the filter. Okay, so I initialize the first value of the filter. So here I run the filter for a fixed number of iterations. We will see later that we can introduce some automatic stopping criteria. We will have time to see that in detail. So in this case I chose, because I know the problem, I think that 4 iterations might be correct, and we will see if it's enough or not. So for each iteration I have to compute x hat, okay? So the correction to the state, update the state and run it again. So the first thing I do is that, as you know, the equation that we have to solve is this one, okay? So we need all these pieces, okay? So I need y, for example, okay? As you know, y is the difference between observed and computed observables, okay? So to do this, what I have to do, I have to compute the trajectory with the initial guess I have, and compute with this trajectory the computed observables. So I repeat the step that I did again before, sorry. So I compute x and v with the equation, the analytical expressions. If you didn't have analytical expressions here, you would have to integrate the trajectory, but in this case we are lucky. Then I compute the observables, as we did before. So we have all the expressions, we can do it for each time step t. Okay, so at the end of this for instance, we have all the trajectory, x and v, and all the observables, range and range rate. So, another part of the equation that I need is the H matrix, okay? So, as you know, the H matrix is the mapping matrix that is composed of all the H tilde, okay? So, to do this, since this is a task that I will have to do at each iteration that doesn't need to be written here explicitly, I can define a function that is called H tilde, as it is done here. It is a bit small maybe. I don't know if you can see it. Oh. Okay, I will paste it here. Oh. I paste it here just so that you see. Okay. This is a simple Matlab function in which I compute H tilde, okay? We have seen it in the previous slides. I take them again here. This is the expression of H tilde, okay? H tilde is computed at each time, okay, on the reference trajectory, meaning on the computed trajectory, okay? So we have to write this matrix at each time step, computed correctly. So everything depends on x, rho, and v, okay? So we can define this H tilde, okay? But it depends on x, v, and h that we use to define rho, okay? So it's very easy because we have the term on the diagonal are the same, okay? It's x over rho, and here it's 0, and here we have the term of diagonal that is v over rho minus x squared v over rho cubed, okay? So we use this function here to compute at each time step each H tilde, okay? So now it is important to remember how H tilde is factorized, because here in this case I have, as I said at the beginning, I have a switch to decide if I use only range rate, or both, okay? So if I use only range, remember that H tilde is composed by the partial derivatives of the observables with respect to the state, okay? If I use only range, the observables are only the range ones. So I will need only the partial derivatives of the range. So taking again H tilde, I will need only the first row. You see, here on the first row I have all the partial derivatives of the row of the range. On the second row I have the partial derivatives of the range rate. So if I have built the H tilde function in order to give me the full H tilde matrix. If I use only range, I will select only the first row of H tilde. If I use only range rate, I will select only the second row of H tilde. If I use both, I will take all the H tilde matrix, okay? So, here, for each time step, I compute H tilde, okay? Then I compute phi, I will go on this, and then I accumulate the H matrix, okay? Because, as you remember, the H matrix is composed by, I'll find it, okay, here. The H matrix is composed by all the h tilde times phi. Okay, this should be clear. So at each time step, I compute h tilde, I compute phi, I multiply them together, and I put them into the h. Okay, so how do we do this? As you have seen here. Okay, for each time step, I compute the h tilde matrix. Okay, and I select only the row that I need, or both rows. Okay, I have the h tilde, I need the phi. The phi is the same thing as before. For h tilde, I have defined a Matlab function that just computes phi. You know that phi, we have its analytical expression, so we have it here. So this function just gives me this matrix here. Okay, so again, for each time step, I compute h, I compute phi, and I compute h tilde times phi. Okay, this is the, let's call it the ith block of the H matrix. This Matlab expression says, okay, take H matrix that you have, and at the first step it's empty, and vertical stack, so put in a column order this other part. Okay, so I will have, at the beginning it's empty, at the first iteration here it's empty, so it adds only this block. At the second iteration it adds another block to H, etc, etc, etc. So at the end you will have H with the correct dimensions that are the number of rows is the number of observations, the number of columns is the number of state parameters. Okay, so coming back to our expression, we have computed y, we have computed h, the only thing that is missing is w, okay, and then this inversion. So w, it's easy because as I told you, in this case we will use an identity matrix. Okay, so okay, here I just compute the residuals. Okay, here are some statistics that we will introduce later. Now you don't need them. Also this part, it's not needed now. I compute just the mean, the RMS, and the sum of squares. Okay, because all I need is defined here, because the weighting matrix is, maybe I skipped it. Okay, in this case it's just one. Okay, it's very easy, but in principle you should build a matrix. Okay, I think I've done it after. Here, okay, here I build the weighting matrix. Okay, so again I have a switch on the case if I use only range rate, or both. Okay, in the case I use range, we have said that we will use only uncorrelated observations. So in general, also if you don't use one as a weight, you will have a diagonal matrix. Okay, so the way to do this is to build an identity matrix with Matlab. Okay, this is this function I, with dimension number of points, of course. Okay, because the weight matrix has the dimension of number of point times number of point. And I just multiply each element dot star. Okay, this is the element-wise multiplication of Matlab, times the weight that I want to assign. Okay, the same for rate. It's a bit more tricky for the both case, because remember we have ordered in the residuals, and you can see it here. One observation of range, one of range rate, one of range rate, and so on. So they are mixed. So I have to build wisely this matrix, because here for the number of points, the odd elements will be the ones relative to range, and the
even.
Thank you. Sorry, quindi the even elements are the ones relative to range, and the odd ones are relative to rate. So the last thing that I have to build is the y vector, that is built in exactly the same way. Okay, because I have computed before the residuals that are, as we have said, just observed minus computed. So if I have only range, y equals only to this column vector, that is y range. If I have rate, y is equals to this column vector, that is range rate. If I have both, I do the same thing. I build them accumulating. So for e in number of points, I define y as an empty vector, and then I stack all the values, one of range, one of rate. I start again, one of range, one of rate, I start again, and so on. Okay? So this is what all the blocks that we needed. So now we can finally perform the inversion, that is this one. So x hat, I call it the x0, okay, is h transpose, this is the sign of transpose in Matlab, times w times h to the minus 1. Here you can see this division. It is the same thing in Matlab. You can write this is exactly the same as, okay, Matlab will tell you. If you try to write this, or also to try
a to the minus 1.
Yes. Also, if you try to write this one, Matlab will tell you, okay, you can do this if you want, but this is more efficient. Okay, a backslash b. Okay.
I prefer the inverse just to show that you have to compute the inverse.
Each time I write the inverse, and then I remember, because Matlab will tell me how to do it this way. You can see here that Matlab says, okay, it can be slower and less accurate, etc. Okay, but it is the same exact thing. Okay. Here, you have not seen already the covariance matrix.
Of course.
You have seen it. Okay, yes. Perfect. So, as you know, this part here, the inverse of H transpose WH, is called the covariance matrix. The covariance matrix, we can call this covariance matrix if and only if we select the weights correctly. That it was what I was saying before. Selecting the weights correctly, meaning weighting each observation with its noise. Okay, so if you know the noise level of the measurement that's recorded the observations, you can use it to write the W matrix. Okay, if you use these weights, then H transpose WH to the minus 1 is a covariance matrix. Otherwise, it is a matrix, but it is not a covariance matrix. It has not the statistical implications of a covariance matrix. Okay?
Well, true and not, because you can define a covariance matrix with the weights which are not the one which comes from statistics. What this expression gives you is the formal covariance matrix. But as I told you, in navigation, there is this old way of saying, if you see a covariance matrix, first multiply by all elements by 10 and then start believing it. So they are all covariance matrix and you have associated errors to them. They are not the formal covariance matrix, and formal in this case means the most optimistic one, which is based on the assumptions that the noise is white and Gaussian, and that your dynamical model is perfect. And this is the reason why navigators tend to use covariance matrices which are larger, the elements are larger than the one that come out from this expression.
Because in principle you can talk about formal covariance, as Professor said, only if your residuals are perfectly white, they follow exactly a Gaussian distribution with zero mean, etc. In the real case...
And you have a absolutely trustful dynamical model.
Of course, of course. Yes, you take into account all the possible effects that can perturb the motion of the spacecraft. So, since in the real case this cannot be done in most cases, this is what you do. You take this matrix, so the inverse of H transposed WH, and then you say this is a covariance matrix to be trustworthy, we multiply it by 3, by 4, etc. Okay, so at this point we have our x hat, okay, so the estimate of the deviation of the state. The last thing we have to do before starting the next iteration is to update the state, okay. So our new initial condition will be the old one plus the deviation that we have just estimated. The same for v, the old one plus the estimated one, okay. We will go through the sigma, etc. later. So for the moment, let's see what happens if we run the filter with these conditions. So the weights are identity, we are using only range observables, we are starting from a solution that is, I recall, I write it here, 4 meters, 1 meter per second, okay. So let's see what happens. I should have computed everything before, so it should work. It's a bit slow because the live scripts of Matlab are a bit slow. Okay. So what we want to see now are the residuals, of course. Okay. So observed minus computed, to see if we have converged, the magnitude of the error, and so on. So I go, it should have computed everything. So let's see. This is only things that I use to plot the results, so it's nothing that I need to explain you, just print something on screen and so on. Okay. So here, at each iteration, I print on the screen the mean and the RMS. Okay, now we are using only rate, I believe. Also, okay. So you can see here, this is the nominal value, okay, meaning the value, the first guess value. And this is the delta that I have computed at first iteration. So the first iteration has concluded, and I have estimated the deviation of the state. This deviation tells me, okay, add minus 0.9 to the nominal value of 4, and add minus 0.75 to the nominal value of 1, okay? The second iteration continues. As you can see, the delta values are becoming smaller, so this is an indication that we might be converging, okay? The corrected value goes, the corrected values, of course, is the nominal value plus the delta solution, okay? So this is the value that I use to start the following integration, the following iteration of the filter. So we go on with the iterations. We can see that the deltas are becoming smaller and smaller, so, and the values are stabilizing, this one around 3 and this one, let's say, around 0, okay? And so we can see the residuals. So this is the first iteration, I call it 0, okay? You can see that the mean, it's small, but it's not 0, okay? It's 1.87 times 10 to the minus 4, and we still see a trend. This is what we have plotted before, because these are the residuals before the first iteration. Remember that I compute the residuals before the iteration, okay? Because I have to compute the residuals, observed minus computed observables. So the observed, I have them, they never change, okay? We loaded them from the text file. While the computed one, they change at each iteration. Each time I change the initial condition, the state, okay? So at iteration 1, you can see here that we have still a trend. However, look at the order of magnitude, okay? Here the maximum was 0.1. Here we have reduced the order of magnitude by a factor of 0.15, by a factor, sorry, of 10. Okay, so it seems that it is converging. We can go on. We can see that the patterns are becoming more and more random, and the residuals magnitude is becoming smaller. And I believe that we have almost converged. Yes. Here we can see almost only white noise. Can you see? This is only noise. We have no more pattern, okay? So this is just the measurement noise, okay? We had only 4 iterations because I start from 0. Okay, so it seems that it worked, okay? Another interesting thing to see is the behavior of the estimated values, because we have seen them written on screen, but if you plot them, it's always better. So yes, I have them here. It's just a plot. I've saved at each iteration the value of x and the value of v, just to plot them. So you can see that these are the estimated value, meaning the initial value plus the correction. Okay, so the estimate of the state. You can see that the initial value was 4, and now it is converging. It converged to 3 quite fast also. While the range rate, it took a bit more time, but at the second iteration it was already converged more or less to 0. Okay, also we can see the mean. Here again, these are only plots, nothing interesting. You can see that the mean of the residuals starts from a value different from 0, and then it goes converging to 0. We can see that maybe another iteration would have been not useless, recommended, not useless. Okay, so this was the case in which we used...
And the RMS value, I don't know whether you have a similar plot for the RMS.
No, I don't have the plot, but I have the values. They are related. Okay, what we can do now is to use both sets of observations, of course. So
and attributing real weight.
Yes. Ok, so
e Brandizzi dice potrebbe rispiegare perché nel codice Matlab utilizziamo la funzione switch.
Of course, someone is asking me why do I use the switch function, because okay, as you have seen here, I have structured this code to be for explaining you things, so I can choose between range, rate, and both, just to use them separately, okay, to make more cases. So in this case, it